Okay, so now let's do the same process for our milling tool heads. And before we do that, let's remove the previous part from the bed. I'll show you a little trick here. So when you use an adhesion layer, a TPU layer, one of the things that this enables, besides just grabbing well to the Kapton and grabbing well to most materials, it allows you to easily remove the part and then remove that adhesion layer from your part. So if we spray a little bit of Kapton on the bed just next to the part and allow it to wet kind of around the part, and then take our scraper and just work at the edge of the TPU layer, we can work the acetone underneath the TPU and it lifts it off the Kapton. The capillary effect helps to attack that interface between the TPU and the Kapton. It doesn't actually dissolve the TPU, it just peels it off. And then the acetone also helps to remove it from the PETG as well. Okay. So now when we're setting up to get the offsets for our spindles, one thing to keep in mind is that there's kind of a base offset for the type of tool that we're using. So when we go from the probe to an extruder, the center line of the extruder is roughly the same as the center line of the probe. When the turret moves the probe into position versus when it moves the nozzle into position, the X and Y offsets are going to be somewhere below 1 millimeter typically. There's some adjustment in the locating of that extruder and some tolerance stack-ups that lead to the offset. But in general, the base offset is 0. With the spindles, it's a different situation. The spindle's center line is offset in both X and Y by 6 millimeters. So the center line of the spindle from where the center line of the probe is now 6 millimeters positive in X and 6 millimeters positive in Y. So that's the base offset of the spindle, and it's something that we need to think about when we're setting up to do a probing cycle, to mill a pocket and then probe the inside of that pocket to get our offsets for the spindle. So to start with, I'm going to print another part, but before I slice this model and generate the G-code for it, I'm going to offset these models by 6 millimeters, both in X and Y. Okay, so now we run our post-processor, same deal as before. Okay, while that part is printing, now we can look at generating our cam tool paths. Now, before we go any further, we should talk a little bit about work offsets. So in the same way that tool offsets cause the machine to compensate based on what tool is selected, work offsets allow the machine to compensate for a difference in the coordinate system of the G-code that you've created in either your slicer or your cam package and the coordinate system of the machine itself. So these offsets are also defined in our offsets page. If we scroll down further, we see that we have these different workspaces. So the base workspace of the machine, and when you restart the machine, this is what it starts in, is kind of its absolute coordinate system mode, and that is G53. Now that's not listed here because there are 0 offsets. Now G54 is also what we use as the base coordinate system of the machine. So generally, you're always going to want to keep these offsets, these X, Y, and Z values for G54 at 0 as well. And that corresponds to what a lot of controllers do. So with a normal milling machine, say with a FANUC controller, your G54 is going to be kind of the base coordinate that the machine uses. So we'll talk about this much more later, but in your CAM package, when you define coordinate system 0 or coordinate system 1, both of those for a FANUC post-processor are going to refer to a G54 workspace. So then in G55 mode, here we can see we have our X coordinate set to -12, Y to 0, Z to 108. So if we had that same part that we just tried to print, and we were in G55 mode, so basically if in the G code, if this G55 line appeared before the start of the motion, it would try to print that part at 108 millimeters above the bed and at an X position of -12. So right now, this is just something to keep in mind, that when you're defining your workspace and when you're printing parts, you're going to want to be in G54 mode typically. The G55, G56, these other modes are going to be much more important when we start doing subtractive operations and when we start using rotary axes and vices and other setups. So I set up this model in SolidWorks, and then I'm going to export it to Fusion, because there are a few things to talk about with coordinate systems in your modeling and CAM software as well. So in SolidWorks, I have my adhesion layer, I have my cylinder, and then I have the two of them. And you can see I have this coordinate system 1 defined there. So if I look at how this part is drawn, this is the base coordinate system in the modeling software. So there's my X, Y, and Z orientation, and my center point, my origin is here. But when I export this part, I want to keep track of where my coordinate system is, and I don't want that to be at the outside corner of the cylinder. I want it to be in the center line on the bottom surface. So I created this other sketch here on that bottom surface, and then defined this coordinate system based on that sketch. And now when I go to export this, I'm going to export it as a parasolid, say. I can also do this when I export the STL. So I go to Options, and my output coordinate system, I'm going to select that second coordinate system that I defined. And now I can save that as my centered model. Okay, so now I'm going to generate my my toolpaths, my subtractive toolpaths in Fusion. So let's see. So I'm going to bring in the model that I just saved, upload that. I'll wait for the upload to actually work. The first thing you want to do when you import a model into Fusion, granted I could have just drawn this this model in Fusion, but I wanted to show the steps of actually importing a model. So right-click to start with and say Capture Design History. That's something I often forget to do, and it always comes back to bite me. So now let's check our coordinate system, make sure it came in correctly. So our XY plane is there on the bottom surface. We can turn on our origin and see that it's correctly displayed. Our Z-axis is here, X, Y. So we should be fine there. So now let's go into the CAM workspace, the manufacturer workspace, and define a new setup. So we'll go here, we'll say new setup, and there are several things to think about here. So this is initially where we define the coordinate system for our tool paths that we're creating. And then when we output this G code, we have to tell the machine what coordinate system to associate this with. So what work offset to use with this. So first, let's define our coordinate system. So our orientation is correct. We have model orientation, but our origin is not correct. You can see it's at the top of the part there. So we want to go to our model origin. Now we're at the bottom surface of the part, as we should be. And then in stock, we really don't care what Fusion is assuming for the stock because our tool paths are not necessarily going to be defined by it, so we can just leave it as is. In other cases, we will want to define the stock outlines. In this case, though, let's just go to our post process. Now, this is the work coordinate system where we define the work coordinate system and the work offsets that I was talking about. So if we put a 0 in here, that will generate a G54 in our output G code. A 1 will also generate a G54 in that in the output file. So in both of those cases, we want to make sure that when we run our machine, that G54, those values that I had showed you earlier here, our X, Y, and Z offsets are 0. So if we were to put a 2 there, that will generate G55, 3, G56, and so on. We can talk more about that later. But I'm going to set this as 1 and say OK. So now we have our setup defined. Now all we're going to do is generate a simple two-dimensional contour. We'll do plenty of tutorials on using Fusion with the H-Series, but for now we're going to do one of the simplest tool paths, which is just a 2D contour. So once I select that, it brings up this dialog here where this is like our in Simplify 3D, where we define all of the parameters of our process. So to start with, we need to define what tool we're using. So we'll go here, and since I don't have the library loaded for this part, I'm just going to start from scratch and say a new tool. Description is 1/8 inch cutter. We'll say 1/8 inch flat end mill. And our cutter, let's go back to, let's see, cutter, yeah. Oh, our units, let's put those in inches for now. And define a few things here. Our flute length is, let's say, 1/2 inch. Our shoulder length is about 1.25 inches. Body length, 1.3, we'll say. So this doesn't really matter. This will just tell you, it'll just help you see if you're going to interfere with your part. So it's mostly for crash detection. It's a 2-flute cutter. And now I'm going to switch back to millimeters because that's generally what our machine is using. And then for feed and speed, we're going to run at 10,000 RPM. And our cutting feed rate, we're going to go at 600 millimeters per minute. Ramp feed rate, I'm going to put that at 400. Plunge, also 400. Okay, so I have the tool defined. Actually, one more thing. Let's go back to that, edit this tool. So the one thing that I didn't do is define the tool in my post processor. So it just happened to be correct. It's set to tool number 1. That's the tool I want to use. Now, the cutter is also defined as a ball end mill. So for a pocket, we're going to need to use a flat end mill. If we try to use a ball end mill for a pocket, Fusion's going to give us errors and not let us generate G-code. Since we're doing a contour, in this case, we're okay. And it's actually a ball end mill in my machine. So let me go back here and set this to ball. Okay. Okay, so then we're going to go to contour selection. That's where we actually select the geometry. And this arrow needs to be on the side of the contour that you're selecting that you want the tool on. So in this case, it's going to be on the inside. If I click that arrow, it's going to go to the outside. So that would actually cut away all this material. So we're going to contour the inside. And then this third tab is where we define our heights. So we can either select entities in the model, or we can use some standard definitions. So we could say stock bottom, which would be the bottom plane. So for our bottom height, though, that's the lowest that the tool will go in this operation. I'm going to say selection, and then I'm going to grab this bottom surface. So that's just above that is our adhesion layer, the top surface of our adhesion layer. And so I'm going to add a little extra clearance. Let's say 0.75 millimeters. So you can see that blue plane moved up above the top surface of our adhesion layer. And then for our top, I'm just going to say model top. You can check that the light blue plane there is right at the top of the model. And then these others are feed height, retract height, and clearance height. So feed height is the height at which the machine will use the slower feed rate and not a rapid move to get into position. So let's say 3 millimeters for that. 4 for the retract height, and another 5 for our clearance height above our retract height. Those are all just kind of factors of safety in there that make sure that we're not going to collide with our part. And now for passes, this is where everything in this tab is what we define for the action of the machine when the tool's in contact with the part, when it's actually cutting the part. And this last tab is the definitions of the motion when the tool is moving, not in contact with the part, but moving into position. So here under passes, we're going to come down and click this stock to leave button. And normally you would use this if you were doing roughing passes first, if you're machining a part and you want to cut away material, but then you're going to want to come back and do a light pass to finish it. But what we're going to do is put a negative stock to leave. So we're going to say negative 0.4 millimeters. So that's going to cut 4 millimeters away from the part as it's defined here. Actually, we'll increase that to 0.6 since our offsets are probably going to be in that range. And now we'll also say multiple depths. We'll do a step down of 1 millimeter. So that defines the depth at which each contour is done. So the tool is going to come down, cut a contour at that level, move down again, cut another contour, move down again. It's kind of the opposite. This toolpath is kind of the opposite of the way a 3D print works. Instead of printing a layer, moving up, printing a layer, we're cutting a layer, moving down, cutting another layer. And that sort of layer height is this 1 millimeter here. And then we'll go into linking and just check that we have this ramp selected. This kind of defines the helix that the tool comes down in. So if we use that, you'll see when I generate this tool path, it's going to use this helix that comes down into the part. So instead of doing that, because that's fairly unnecessary, it'll just waste time in our operation, I'm going to get rid of that and just allow the tool to come down into the part. There we go. So now there's just this little kind of entry as the tool comes down and then comes across in a smooth contour into contact with the part. So now we have our tool path defined and we need to output it. So we're going to right click and say post process. And this is where we select our H-Series post processor. I'm going to have to find it here. Yeah, so diabase H-Series post. And in this case, I'm just going to label this as the date. So 6/19 and 1, the first G code that I'm generating today. And then let me say offset pocket. And I want to save this to tutorials. Okay. So I'm going to post process, save it here. Okay. So if we look at the G code now, we just scroll down. Here is that G54 that the post processor inserted. So when we had that work coordinate 0 or work coordinate 1, it's going to put this G54 command in there that tells the H-Series machine to use that work coordinate 1. So I'm going to close this, go back to my control, upload the file. Okay, and now before I run this code, I want to make sure that I go into my offsets page and set my X and Y offsets to 0. And my Z offset is still the same. I definitely don't want to change that or I'm at risk of crashing the machine. So now, before I start a milling cycle, I always want to come into my job status screen and turn my speed factor way down. So whenever you generate new G code, you want to be very careful when you're running a milling cycle because a crash with a milling cutter can be much more damaging than a crash with an extruder. So now I'll go back to my G code files and say start. It's going to say, you sure you want to run this code? Yes. And then it's going to ask me again, are you sure you want to run this? No additional homing will be done. So unlike with a print where the tool or the machine switches to the probe, comes down and probes the bed, with a machining operation, we don't do that. We just start with the coordinate systems that we already have defined. So I'm going to say OK. And now it's moving more slowly because I have that speed factor turned way down. All right, so what I just realized is I typed in 1,000 instead of 10,000 in my spindle speed. So if I right click here and go to edit, I can bring up my G code file and make that change. And then hit save. And now I'm going to restart. So again, it's going to ask me, do you want to run this G code? Yes. And it gives me that warning that no additional homing will be done. So I'll say OK. It's going to move more slowly than typical. Just be ready. Make sure that the machine has the correct coordinate system set. And it looks fine. So now we can go into our job status, increase our speed factor to allow it to cut at a typical speed. Okay, so after the milling cycle finishes, you want to blow the chips away and then check the inside of the cylinder to make sure that the milling cutter cut the entire inside surface, which it looks like it did in this case. If it didn't, then you would go back in and adjust that negative stock to lead that we talked about. So now let's go to our machine control, bring up our touch probe, and then we'll jog to the inside of the cylinder, probe the inside of the cylinder, and then define the offset the way that we did before. Now we can come back to our offsets page and probe the inside for Spindle 1, so fine center. Really any of these buttons would work, but you want to get in the habit of just using the button that is for the tool that we're about to set the offset for, because in the future we'll make this a little bit more automatic. Find the center. It says, are you sure that you have the probe installed and you're ready to go? Yes. Okay. So our probe location is 5.79 in X, 5.24 in Y. So we'll come down and we'll say set offset. And we're good to go. So this was just a first video on the coordinate systems of the machine and on tool offsets. We're going to go into much more detail on all of these operations and a lot more to come.